do that, just give me a little bit of space because bowler is coming to bowl. So I am ready as a batsman and I have to hit a boundary. Hey, but before the bowler is coming, let me ask you a question. So to hit a 6 or to hit a boundary, do I need power or energy, or do I need both? So we'll try to answer that. Okay, so now let's just be ready. Bowler is coming in and now I'm gonna hit like this. I am doing some work. There's force, there's displacement, and like this. Hey, what? Can I ever hit 6 doing this? No, never. Right? So what I have to do? Okay, let's just give it one more try. So now I am once again ready. Bowler is coming in and here's a 6. Okay, so I don't know whether you can see the ball, but that's in 6. Okay, so what we have done here, so what we can see is that in both the cases the work done was same. Work done is the force into displacement. So from here till here the work done is same. But what was the difference? Yes, the difference was in the timing. In the first case I took 5 seconds to do this, but in the another case I just took 1 second to do the same work. So from this what we can say is that not only the amount of work or the amount of work done matters, but with that the time in which that work is done, that also matters, right? So now the time or the rate at which the work is done, what is that called? We're gonna discuss that. Okay, so till now whatever we have seen, we're gonna connect that with electricity. So what we have seen, that not only the amount of work done, well, work done is nothing but the energy, right? So not only the amount of energy matters, but with that the rate at which that energy is getting consumed or getting dissipated, that also matters, right? So the rate of dissipation of energy, what is that called? Yes, that is called power. Okay, so we have that power is the work done per unit time. P is equals to W by T. Now we know that energy is measured in joules and power is measured in, yes, tell me the answer. Yes, power is measured in watt. Yes, so let's write the units here. So we will have 1 watt is equals to 1 joule per 1 second. It simply means that when 1 joule of work is done in 1 second, in that case the power getting consumed is 1 watt. So I hope that this is very clear to all of you. Now from here only, see, work done is nothing but energy, and in this case let's say it is electric energy, right? So we have that power is electric energy per time. Now let's rearrange the terms here. So we will get that power into time is equals to electric energy, right? And since it is power into time, so we can say that yes, it is 1 watt hour. So electric energy is equals to 1 watt hour, and this is nothing but the unit of electric energy. So the unit of electric energy is watt hour. Okay, so once we are done with that, now let me ask you a very simple question. So tell me that what is electricity? Well, this is very simple, that electricity is the flow of charges. Well, negative charge or positive charge? Well, actually it is negative charge, but conventionally we say that it is a flow of positive charge. If you are getting confused here, then I have already made a video on that, you can check that out. Okay, so now we know that charge moves. But now my next question is that from where those charges get energy to move? Well, we don't go and push the electrons and tell them, hey, please move, we want electricity. like that doesn't happen. So we know that for this we have a source and we call it a battery or a cell. So battery creates a potential difference and we also call that as voltage, right? So we have voltage, right? So what is voltage? Now voltage is the work done per unit charge. V is equal to W by Q. Now we can rearrange the terms here. So we have now that W is equals to V into Q, right? Work done is equals to voltage multiplied by charge. Okay, so from right now, the only thing we are going to do is that we're gonna substitute the values here and there, right? So you can just relax and watch this video. Okay, so what we have here, that work done is equals to voltage multiplied by charge, and we also have that power is the work done per unit time. Now what we can do, we can substitute the value of work done from our equation 1 into 2. So what we will get? Yes, power is equals to voltage multiplied by charge per time, right? So we have P is equals to V into Q by T. Now one more thing we can do here. So tell me, what is current? Well, current is the flow of charges per unit time. I is equals to Q by T. Now again we can substitute the value of Q by T, right? So what we will get here? Yes, that P is equals to V into I, right? So here we got the standard equation for the electric power, right? So power or electric power is equals to voltage multiplied by current. Okay, and we can also write the units here. So we have that 1 watt is equals to 1 volt multiplied by 1 ampere. It means that if in our circuit the voltage is 1 volt and the current is 1 ampere, then the power which is getting consumed is 1 watt. Now we can do few more things with this standard equation. So what we have, P is equals to V into I. Now using Ohm's law, what we know? Yes, that V is equals to IR, right? So now we can substitute the value of voltage, right? So what we will get? Yes, power is equals to I square into R, right? So this is the one more equation for the electric power. Now let's rearrange the terms in the Ohm's law. So what we have, that I is equals to V by R. Now again let's substitute the value of I or the current, right? So what we will get, our third equation is P is equals to V squared by R, right? So we have 3 equations for the same thing. Well, they all are the same if you were to think about it. Well, can you guess that why do we need these 3 equations? No, why one equation is not enough? Well, let's say that we have a series connection. Now in series connection, what we know, that current is constant and voltage is difference. Now since current is constant, so using this equation, which is P is equals to I square R, so this is going to be a better option, right? And in the case of parallel connection, in which voltage is constant, so in that case we will use P is equals to V square by R, right? So we have these 3 equations so that we can save our time and we can reduce the calculation. By the way, you can anyway come to the final equation, but just to save our time, we have these 3 equations. Okay, so now before moving ahead, let's just solve one very simple question, right? So here you can see the question. Now how we can solve this? So first of all, write what is given and what is asked. So what is given in this question? Voltage is given, current is given, and what is asked? Power is asked. So now we have to think about a relation between these 3 quantities, right? So we have just read that P is equals to V into I. Now what we can do? We can just substitute the values here, and what we will get? Yes, we will get the answer as 110, and the unit is going to be, yes, watt. Okay, so that was, by the way, very simple question. Okay, once we are done with that, now we are going to talk few more things about the unit of power or electric power. So what is the unit? Yes, it is watt. Well, 1 watt is, it is a very small unit. Let's say if you want to measure the distance between Delhi and Mumbai. So are we gonna use centimeters in that case? No. Meters? No. We will use kilometers, right? So we need some big quantities, right? So here, let's say that we have 1000 watts. So that is equals to 1 kilowatt, right? So we are just trying to derive some new big quantities. Okay, so we have that 1 kilowatt is equals to 1000 watts. Now let's say that this 1 kilowatt of power is getting consumed for 1 hour. So what we will get now? Yes, 1 kilowatt hour, right? 1 kilowatt of power getting consumed for 1 hour. So we will get 1 kilowatt hour. So that was again very simple. Now we know that 1 kilowatt is 1000 watts and hour is nothing but 3600 seconds. And what we can do? Yes, we can simplify this. So we will get that 3.6 into 10 to the power 6 watt second. Okay, and watt second is nothing but joules. So what we get is that 1 kilowatt hour is also equals to 3.6 into 10 to the power 6 joules. It means that if that much work is done, so we can say that power which is getting consumed is 1 kilowatt hour. And this 1 kilowatt hour is also the commercial unit of electric power, and we also call that as unit. On the electricity bill, you might have heard that you have used 200 units, right? So that's what it means. So 200 units is nothing but 200 kilowatt hour. And you should also try to note down the meter readings, try to check out your electricity bill, and you can substitute the stuffs here and there. So what I'm trying to tell you is that you should apply this knowledge practically in your life, because that's what the purpose of this education, right? So be a little bit of practical. That's what I'm trying to tell you. Okay, so now it's a summary time. So let's summarize all the things which we have learned in this video. Okay, so what we have seen? We have seen 3 equations for the same thing or for electric power, which are that P is equals to V into I, P is equals to I square R, and P is equals to V square by R. So these are the 3 equations for electric power. And we also saw that the unit of power is watt, and for some huge quantities we have that 1 kilowatt which is equals to 1000 watt, and we also saw the commercial unit of electric power which was 1 kilowatt hour, right? So that's it for this video. I hope that you understood all these things. If you did that, then don't forget to hit the like button, and please do subscribe to my channel for such more informative videos. So I'll meet you in our next video. Till then, thank you very much for watching.